Welcome. After learning about some techniques to estimate the pressure and the quality of natural gas, we shall do some few problems on these. So, in this lecture, we shall be learning that on tutorial on temperature and quality measurements in natural gas, and we shall be learning about the estimation of temperature and the quality in natural gas. So, this is the first problem on the temperature estimation. In this we have used a data from platinum resistance thermometer, which says that it gives a reading of about 38.6 ohms at certain temperature, and it is given that at 0 degree centigrade it is 100 ohms. That is, this platinum resistance thermometer gives a resistance of 100 ohms at 0 degree centigrade. This 100 ohms is not fixed. Different platinum resistances may give different values of the resistance, and because it is 100 ohms, so this kind of resistance thermometer is called PT 100. PT stands for platinum and 100 stands for the resistance at 0 degree centigrade. So, that means we are using a PT 100 temperature sensor for this kind of natural gas. So, this PT 100 gives a reading of 38.6 ohms at certain resistance, certain temperature, and this resistance is given by Re. And we have been given these values of the various coefficients which are used for the converting the or correlating the resistance with the temperature for these platinum resistance thermometers. So, here this is the calendar Van Dusen equation which takes this ABC, and we find that in this expression the temperature is coming in terms of T to the power 4. So, this is a quartic expression which needs to be solved to find out the value of temperature for a given value of relative resistance, that is Re by R naught. So, this is a nonlinear equation in temperature. So, we may use some nonlinear technique of problem with this root finding method, but so there are two types of method we can adopt for solving this expression. So, let us go by first method. In the first method, what we do not go for a root finding method, but we go for iterative method by substituting the values successively in a modified expression. So, what we start with is this: we first neglect the nonlinear terms in the Van Dusen equation, and here we have this expression for temperature. This temperature, this T1 represents the first iteration temperature, and here we find this is the Re by R0 minus 1 divided by A. So, we put this linear expression to find out the value of first estimate as minus 155.6 degree centigrade, and now because it is nonlinear, what we now do that we put this expression for this modify the equation a bit, and we put this expression, and now what we do that this in the RHS we put this value of this minus 155.6, and after putting this value again we find the value of the temperature as a second iterative temperature, and then we find that this temperature gets modified to minus 149.61 degree centigrade. Now, with this temperature again we go back to this expression, put this temperature values here, and again re-estimate this temperature, and that way we keep on doing this iteration, and ultimately we find that we are carrying out this iteration, and we find in 4 or 5 iterations we almost approach a constant value, and because these values are almost same, so we take the final temperature to be minus 150 degree centigrade. So, this is a very simple method that where we linearize the expression and go for a substitution method successively to get the root of the equation. So, this is one of the ways. Now, we may also go for a direct solution of this quartic equation, and in this direct solution we can use the standard Newton's method, and if I apply this method, and for solving this you can do it either manually or you can code it. You can also use MATLAB code to solve this expression. So, if you do it bimanually or by some MATLAB or other Fortran code or some C++ code, you will find that you get these 4 roots of the equation. So, these 4 roots are given by this, and you find that first 2 roots are obviously not right because they are giving imaginary values. So, they are rejected, and the third one is not imaginary, but the value you see it is degree centigrade. So, this is much less than the 0 Kelvin. So, we know that absolute temperature can never be below 0 Kelvin. So, this is also taken out. Only the fourth root is can be a feasible one. So, we take this approximately, this is as 1 minus 150 centigrade. So, we see that by adopting 2 different methods, we can arrive at the same value of the temperature. So, this tells us that our actual solution does not depend or must not depend on the type of technique we are using to solve these expressions, nonlinear expressions. So, with this we find that we get the temperature of the natural gas as minus 150 degree centigrade. Now, we go to another problem on the quality estimation. When we say quality, as we learnt earlier, quality means that what is the fraction of the liquid and vapor in the natural gas, and in this case we are defining the quality in terms of the amount of liquid. So, in this problem we have been asked to determine the quality of natural gas in terms of rate of liquid flow in GPH, that is gallons per hour, based on these field conditions. And please note that these field conditions are the same as we did for the earlier solution for the finding the flow rate through orifice meter of natural gas. So, we have taken the same values here, and we do many these unit conversions, and we find that we get this expression for the liquid flow rate, and here we have been given the value of C in terms of FB, FR and FG. Now, as we discussed under the flow rate for natural gas through orifice meter, we find that the same values of the correction factors FB, FR and FG are also used in this expression. So, we go to this expression for FB, and FB is obtained from this particular chart. Here we have the orifice diameter, and here we have nominal diameter of the pipe. Depending on that, we find out the value of this factor, and this can be obtained from this particular reference here, and we get the value of the FB for this, and then we go for another chart for FR. This FR has been obtained from this particular chart. Again, it depends on the orifice meter and the nominal size of the pipe and the gauge of the pipe. So, from this particular chart we locate the orifice diameter, the nominal diameter, the gauge, and we find out the value of the factor FR. And then lastly, we have the value of the FG, this obtained from the specific gravity, which we also find out earlier, and this is coming as 1.2910. So, with these values, what we do now, we have all the values with us, and we plug in the values over here to find out the value of C, and this C value is then plugged in into this expression, and HWPF are given in the problem. This is HW is the height of the water column, and with this we find that the liquid flow rate in the natural gas is coming out to be 122,810.5 gallons per hour. So, this is the flow rate of the liquid. Once we know the flow rate of the liquid and once we know the gas flow rate, now we can take the appropriate ratio to find out the fraction of the liquid in the natural gas, and that is how we represent the quality of the natural gas in terms of the liquid flow rate. And these are the some references from which you can get the more detailing and the data to solve the this temperature as well as the quality of the natural gas. Thank you.